Hi everyone. So my name is Aurel from Scroll, security lead. And I'm joined today by Guillaume.
Hi.
Here. Guillaume is a developer on zkEVM, the Ethereum node, so that has the regular EVM inside. And here, I'd like you to learn about the zkEVM. So what is Scroll? So Scroll is a zk rollup, so for scaling Ethereum, and it attempts to be EVM equivalent as much as possible. So that means it can read the bytecode from the Solidity compiler and modify it, and it even calculates the gas and as many details as possible. So vision of Scroll and the zk rollup. So again, scaling. It's all in the open, everything open source. And everything is meant to be decentralized. It's not easy to do, so it will take time, but teams are working on decentralization.
Yeah. What about secrecy? Is that also a goal?
No, that's not in scope. So the model of the EVM is really difficult to make private because it's an account model. And if you want to do a private protocol, let's say, the other people, they need the state to make their own transaction, right? Mm-hmm. So if I send a private transaction that is kind of encrypted, other people are not going to be able to continue and spend their own money or do their own action contract. So it's pretty difficult to make a private EVM. You need another model, basically, of computation. And it is possible, it's just very different. So how does a rollup work? So we have mainnet. So there's going to be a smart contract on mainnet. That this smart contract, it holds basically the state root. So I hope you're familiar with Merkle trees and such. So it's the root of the current state of the rollup, and the smart contracts wants the next state and just updates the next state like this, and that will commit all the transactions from the rollup layer. So the rollup is another chain with a whole lot of transactions happening there on layer 2, and we'll send a proof to the mainnet contract that all of those transactions are correct, or that the side effects are correct, and this smart contract will just update this root, which is very small compared to the amount of computation that was happening there. The data of the transaction is still on mainnet, on Ethereum mainnet. So the decentralization of Ethereum will guarantee that this data is always available. So you can always connect to some Ethereum node and get a compressed form of all the transactions of the rollup. So it's much smaller than the transactions on Ethereum. For instance, they don't have signatures and they are compact in some way, but they are enough to reconstruct what's happening on the rollup. So that's the contract, the proof. So in the architecture of Scroll, there's a relayer that reads this data or updates it, the transaction data that I just mentioned, and it also synchronizes the contract, share the proofs with it, and the sequencer. Sequencer, it means it's like GEF, right? Mm-hmm. It's actually modified GEF. So it's what you connect your MetaMask to, and it can tell you what is your balance, and it can accept your transfer transactions or your contract transactions, and it's going to prepare them into a block, right? So from there, it sends it to a prover. So a prover is a separate component because it's very big. It's like a supercomputer. It's that generates zk proofs. Goes back to the sequencer and relayers to synchronize. Can you say something?
Several things. So the prover does not basically blindly trusts what the sequencer is doing.
Yeah, it's a service for the sequencer, right?
Okay.
Here is my block and give me a proof. It's a big machine with a lot of GPUs inside.
Okay.
And right now, so in this version of Scroll, right, what's running on testnet, it's basically all together, right, in a cloud. So that's the same organization. But then not shown here, it's meant to be decentralized. So you will have everybody can run their own prover and be paid for it. And they just have to accept the block, run the proof, send the proof, and if the proof is correct, they will be rewarded. And the sequencer has something to satisfy the contract on mainnet.
And so if the sequencer is some kind of modified Geth, what consensus algorithm does it use? And is that part of the thing that is being proven by the zkEVM?
Yeah, so again, that's two phases, right? That's the phase where it's not decentralized. Mm-hmm. It's not decentralized, but it's trustless in correctness, right? So the sequencer cannot cheat, cannot make fake transaction or something, or steal someone's money, but it's centralized, like you have to send information to it. And then in the decentralized phase, what's the question?
What kind of consensus?
I don't know, honestly. There's a team at Scroll that does research about that. Mm-hmm. So it's in research.
Right, but will the aspects of the consensus will they also be proven, or is it just the execution that gets proven by the prover?
Whether the mainnet verifies the consensus of the rollup.
Right.
I don't think so. I would call it the third phase then, because this is even more difficult. But that's also possible. That's something, for instance, Mina does that. Mm-hmm. It's a zk proof of consensus as well. No, but first you have a consensus of the rollup, and actually the goals and the constraints of the consensus of the rollup are different than this of a blockchain. So that's why it's an area of research. Mm-hmm. It doesn't have to do the same things, but that's not my expertise.
Right. I don't want to trail off too much, but what are in what respect? Okay, it's not your area of expertise, so we can.
But the important part when we say we decentralize the sequencer, it's about censorship resistance, mm-hmm. right? So if a sequencer doesn't like you, you can always find another sequencer to include your transaction in some future block. So that's decentralization of the sequencer.
And a quick question: if someone you are a sequencer, and I want to prevent you from. So you're a sequencer, and you refuse to censor me, for example, but someone else doesn't want to build on top of your proof. Can they do this? Can they block you this way?
To build on top of your proof,
you push your data, you push your proof to the rollup, and somehow can they decide I'm not going to build on top of that block on that?
Well, that's the difference of consensus between mainnet and rollup, right? Because really we rely on the consensus of the mainnet. Mm-hmm. So once this rollup contract says that there's a new block,
right.
You don't have like a rule of longest chain or something like that. You don't have another chain, right? It's when the mainnet contract has approved the block, then that's the top of the chain.
Okay.
So everybody builds on top of it.
And the only thing that goes into the rollup contract is to say the proof is correct. You can't say the proof doesn't follow my consensus rules.
So the oh yeah, it's more the contract that will enforce the consensus rule, right?
Right.
So in the not decentralized way, it's simple. It's just like an admin, right? It's a privileged account of a sequencer or a multi-sig, and that's like consensus. So the contract sees from where it accepts it. And if we do a decentralized consensus, yeah, the mainnet contract has to verify that this comes from the consensus protocol. So maybe it's not verified in zk, but verified in smart contracts. But again, I'm not completely sure. And this is in research. So I guess we'll have more communication about that in the future for sure. All right. So now let's focus on the zkEVM that this contract wants. Or maybe I can check for questions first, in case there's anything. I'm not sure.
Not yet.
Yeah. So Anna, just tell us if we should go to the chat. Sometime.
I will. I'll jump on.
Thanks.
Or if I need to shut up.
No, it's cool. Just one thing, when you're talking, make sure you're in the screen.
Okay.
Yes,
yeah.
Exactly. Because you were a little bit off earlier. But
this is a directional microphone, so it should be front.
Cool. Keep going.
So the zkEVM now. So the particular one that we're talking about, it's a project of Ethereum Foundation privacy and scaling exploration and a collaboration with Squall. So a PSC group is interested in that because it's to make proofs about or validity of the mainnet block. So to make a kind of lighter nodes, right? So eventually, maybe in some years, we can have lighter nodes that just verify the proof. Someone makes a proof, and then you only verify the proofs of the blocks, and you don't have to have all those like terabytes of data to verify it yourself, however big the node is these days, right? So that's what that's the goal for Ethereum, and for Squall, the zkEVM is part of the work. So, but that's the same code base mostly. So what does the zkEVM have to prove? So if people have ideas, what does the zkEVM do? Or if you have ideas?
It executes EVM contracts.
Yes. So it has to execute the contracts. So step by step. So first gets the transactions, right? So it has to verify the transactions, like this encoded, like compressed transactions.
I mean, execute the transactions first, and then if you're on the producer end, and then verify them if you're on the receiver end. But
yeah,
I assume if you're using zk rollups, you don't really have to verify. I mean, you're not going to verify directly like it's currently done in Get. You don't re-execute the program.
Oh yeah, it does. It does. So the zkEVM kind of executes the program
when producing blocks.
Yes.
Not when verifying.
Not when verifying.
Okay.
So the verifier is a kind of verifying a proof is kind of like a compressed way of verifying the entire thing. When you make a proof, there is a circuit, and you can think of the circuit of the computation inside of the proof as being the verifier, like virtually, right? It's like a virtual verifier that you try to convince as a prover. And this verifier is, this virtual thing is executing the contracts step by step. Right? So when you have your Solidity smart contracts, it's in bytecode, right? Starts at bytecode index 0 and goes to the next one and the next one. And sometimes it jumps and so on, right? So it has to do with step-by-step execution. What else? Well, it has to verify the bytecode also. Because where does the bytecode come from for the zkEVM? It's
You're still asking me?
yeah, or
maybe you want to ask the chat.
Yeah, or maybe some people want prove the execution trace of the state transition. Yeah, that's good way. And I was saying, yeah, the bytecode, where does it come from? It's the prover gives the bytecode, and the verifier wants to do what? Basically, recalculate the hash of the bytecode. So because the accounts on Ethereum, so a contract account, it stores only the hash of its bytecode somewhere, right?
Yeah, I mean, you have to. I'm talking about guess. You have to store the code, of course, but yes, the account only has a hash reference to the code that is stored somewhere else.
And when there is a call to it, you have to go to your database, load this bytecode. So a prover here does the same, loads the bytecode, but then you have to also recalculate the hash because it's a sort of like temporary in memory of the zkEVM. So it recalculates the hash to see that it's well, but the question which is too high level for now. We'll go back to it. What else does it need to do? It needs to recalculate the state roots.
Yep.
Because when we go to the world contract, we're only going to give a root, right? Like 32 bytes of Merkle roots.
Right.
So, well, the contract, it has the previous root and the next root, right? So that's like 32 bytes each. So the zkEVM has to, whatever it reads from storage, it has to check that it is included in the old state roots. It has to do Merkle paths. And the things that it changes, it has to do a Merkle path into the new state roots. So it has to verify all its storage access.
So all this, there's a lot of information associated with the execution of a contract, and the zkEVM needs to validate outside of zkEVM in the regular EVM. There's a lot of cryptographic primitives used, like let's say classic cryptographic primitives used to validate that the data you are passed is correct.
Yeah.
And you need to do the same thing in the zkEVM, the same kind of verification, but presumably in a more zk way.
Yeah. So the zk part, it has its cryptography, and inside there is cryptography, right? The actual thing you compute is cryptographic, like hash functions,
right?
In the Merkle tree, for instance, and verifying signatures from the transactions. So it has to do that as well. So it's also cryptography. And it makes sense. So every time you have a zk something, a zk circuit, what are you going to do inside? There is always going to be some cryptography inside, like to communicate between the circuits and the outside, right? So there is maybe a lot of data inside of a circuit that is being proven something about with English, and but it has to calculate a hash of it, some kind of commitment to the outside, right?
Yeah.
But the outside knows what the circuit was talking about all this time, like the state roots, or also the hash of the transactions, right? So it's always like this, but the zk circuit, it always does cryptography inside. And that's why we are so concerned about finding primitives that are efficient in zk. Like, so for hash functions, everybody likes the Poseidon hash function, for instance.
Yeah, because I mean, the problem with the current state of Ethereum is that we're relying on some cryptographic primitive, which is called the Ketchak, which is one of the precursor to SHA and SHA-3. And this is something that really doesn't play nice with zk circuits.
Yeah.
So do you use other primitives inside, like, because you have control over this this sequencer, you could decide to change something while not changing the functionality. You could change the flavor of some hash functions.
Exactly, yeah. And it goes back to what it means to be equivalent. So if we change the hash function of the state roots of the Merkle tree, is it still equivalent or not? I think so.
It's equivalent, but it's not compatible.
It's not compatible on on the byte, like serialization.
Right.
So.
Yeah.
But from the point of view of a smart contract, the contract doesn't care. It just says, I want to read and write into the storage, and it doesn't even have to know that there is a Merkle tree or hash function.
Absolutely.
But there are other places where the smart contract explicitly wants a ketchup, right? And if it's not a ketchup, it's a different value, and it's going to be incompatible with something else.
Yeah, that's true.
So there are both. So in the zkEVM, there are both hash functions. There is the ketchup one, which is a bit more expensive, and the cheaper one, which is the Poseidon. So it has both, depends on places. So Solidity does a lot of ketchup inside, right?
Yeah.
Every time you use the storage, it does the ketchup to find the key of storage, and this we have to do as well.
You have a question?
I have to move here? No?
No, it was right here. Can you discuss scrolls work on GPU?
Yes, we have.
Actually, just one thing about the questions. If you might want to start at the bottom. So if you look, there's some that were answered. That was from the previous session, and then you might want to work your way up. Just FYI.
Oh, wow.
Yeah.
No,
there's like 5 questions.
There is a Q&A tab, but this is still about the other. So here I'm in the chat tab, right?
You should say Q&A. If you click on Q&A.
In Q&A, this is.
Go sessions, Q&A.
Oh, you have to go at the top. Oh, this is so confusing. This is the opposite of every other product.
Well, we've been using it for a while, but yeah, do you see it?
It's just like zkEVM. It's a flavor.
It's another flavor. So at the top, so GPU. So yeah, we have an entire team working on the prover here, which uses GPUs. So that's a lot faster. Yes.
I need to interrupt you real quick. You do need to read out the question that you're answering, because for the video, we won't actually know what you're reading. So say the question, give the answer, and just to note, there's four of them there that you want to answer.
So someone is asking about Scroll's work on GPU acceleration. And yes, there's an entire team working on that. So you have basically a prover implementing in CUDA. And a lot of the zkEVM, a lot of improving can be done in parallel. Not all of it, so there are still bottlenecks, but a lot of it can be in parallel, and on GPUs it's very effective. It's all arithmetic, so so it's really important, yeah. And now that if you move away from proof of work, there are a lot of GPUs available, right?
Yes.
Yeah, and we use ridiculously big GPUs, whatever is available. Privacy feature. So does the zkEVM have privacy features? So we explained that no, because of the account model of the EVM. It's really difficult. What are the security challenges you are facing? We'll face in the coming months. So this is very actual. So we're running the security audits now. It's starting now. And there are so many. I have a lot of slides about that. But the challenges. So one of them is you want to be deterministic. So you have the old state codes and you have the transactions. And that implies the new state. So you have to be very careful. There are so many steps, and it has to be all deterministic into the new state. Because otherwise, we have the problem I explained earlier, that other people will not be able to make new transactions or to continue the rollup because they don't know if you can generate another state that is not deterministic, and that's different what other people would want with the honest software. Then other people will not know what is inside of the state, and so they cannot make Merkle paths anymore. Right? So very important to be deterministic, and then of course important to be correct, right? Like all the rules of the smart contract must be implemented. There are so many quirks, so many. So that's then you have another security aspect, which is the security of the smart contracts. So the Solidity compiler and the smart contract developers, they make some assumptions about how the EVM works. So of course there is the spec, the yellow paper, and then you have, but there are also other assumptions, a lot of details that they rely on, and they rely on the latest EIPs and whatnot. So you want that when people deploy smart contracts on the rollup, that it works the same. It's as secure. For instance, if a smart contract needs to run a big transaction sometimes, right, and that uses a lot of gas, right? And of course, the developers have to be careful that this big transaction fits into a mainnet block, right? But now they have to be careful also that it fits on a rollup block, right? So ideally, it would be as big in capacity, but if it's not, they have to design this smart contract to have small enough functions. There are so many security. That's the main thing, right?
And you also, you also have potentially, because if you're using Poseidon, so I mean, most people trust it, but there's still some suspicion about the eventual security that Poseidon brings. Is that also something you? I mean, I assume you must look into that, into the security, the safety of the core primitives you're using.
Yes, yes, and that's two things. You need to believe in the cryptography of the hash functions and the cryptography of the proving system also. And you need to trust also the implementation. Right?
Yes.
The implementation of it in circuit. And again, both PSE and Scroll have teams of cryptographers looking into this. So that's of crypto. What else in security?
Yeah, I mean, maybe we can get another question.
Yeah, but there are a lot of security questions. Any other question, or maybe we move on to the next topic.
There was a question at the top, I think.
Is the communication between sequencer and relayer real time, or is it scheduled? I don't know. I don't know what to say.
Well, I mean, it's got to be scheduled at least between the relayer and the sequencer, depending on how the sequencer works. But if it's like block based, it has to follow the clock of the block production. So somehow it's at least somewhat scheduled, I assume.
Yeah, I'm not sure what is meant by scheduled, but it is. I can show something else. So presentation from here, and you see the sequence. It's a pipeline actually of proof generation like that. So T, that's trace. So that's a block. That's all the mini steps inside of a block with all the transactions. And
okay,
you have here a block.
Right. So basically, if I understand correctly, the sequencer, is really just like gas producing blocks, and then the whatever you call it, the coordinator will generate the prover. Basically, will follow the chain, maybe a bit behind, and produce proofs, possibly for a series of blocks to catch, to keep catching up. So yeah, it looks like indeed it's kind of. I mean, it's both real time and scheduled in this way, I assume, because it's scheduled in the sense that blocks get produced with some regularity, and then it's real time in the sense that you still need to be able to generate proofs that requires a lot of computation. So it's on the it becomes available when it's ready, basically.
Yes, and the provers, or we call them rollers, they really work as a service, right? They're not the one communicating with the chain. It's the sequencer requests, please make me a proof, and when it's there, then it can do. But so again, this is not my expertise, so maybe I will say something wrong, but I think they are, like this, right? There are phases. So block is proposed. Then you have the transaction data is committed, so it's available. Everybody can see the transaction data, and it's finalized once you have proven what's the result of those transactions. So there is like a multi-step like that. But I don't want to comment more on that because I'm not so sure. I'm working more on the inside of the zkEVM. All right.
Yeah, maybe you want to show some traces.
Yeah, maybe let's move on. So, we were still talking about that. So we said, I think we said that as well. So then, what's inside zkEVM? So the trace that comes in. So that's all the steps that every transaction does. Run the smart contract, read and write, and transfer tokens and such. So that's all the steps that it does. And this goes into a circuit. So it's the trace is sort of encoded in a way in a circuit. We call this the witness. Now, zkEVM is not just this processor of bytecode, right? It's a full computer inside. It has a CPU, kind of CPU, but it also has a memory, it has a stack, and it has the permanent storage. That's an SSD compared to one that looks the same these days. And it has other things. So, for instance, the Ketchak and Poseidon and so on, those are separate circuits. So there are quite a lot of them, and with different specialties. So it's like coprocessor in a computer, right? That's specialized for hashing. Yes. The storage circuit is specialized to write those Merkle proofs and so on.
You got a question? Let's do it.
So what's the constraint size of the aggregation circuit? Well, this is getting very specific.
They're trying to steal your idea.
Well, it's all in the open, right? So you can read the code. Yeah, what I didn't mention yet to go for this is that those are the EVM circuits that makes a proof, or maybe we can think of it as multiple proofs. And then there is an aggregation. So the problem of the zkEVM proofs, also the zk part like compresses a lot. It's a lot of computation that's compressed into a small proof, but even that is still too big for mainnets. But even verifying the proof is too much for this smart contract, or too expensive, and it's too big. So there's another circuit which verifies the zkEVM and then makes a proof that it has verified it. Right? So that's a 2 layers thing, and this proof is smaller, and this is what goes to the mainnet contract. And then in the mainnet contract, there is also a verifier, but that verifies the small proof. And this aggregation here, this is also very big. So it's probably maybe half in cost or such. Well, it can be tuned, so we can change the parameter and change like which one has the most constraint. That's because we use Halo 2, and Halo 2 is very flexible. So if you want, you have basically a kind of parameter that you can tune. That's what I call the width, and and you can choose if you want a faster prover or a faster verifier, right? So the answer to this question is depends. We tune it to optimize it, like how many, how big the aggregation is. So another question.
Oh yeah, you have to expand.
So is there a checksum mechanism for the correctness of information sent? Right. Sure, I understand the question. Checksum mechanism. I mean, basically, zk circuit is a very big generalization of the checksum. It's so yes, it verifies the correctness of everything, of all transactions there.
But by the way, that's a question I had for you. Does it verify, or does it leave it on the blockchain to let anybody else, kind of an optimistic roll-up kind of thing? Does the contract do the verification, or does it actually just put the proof and someone else can come and say and flag the proof as invalid?
No, so this is the difference with optimistic rollups. It's no, there is no someone comes to do something. If the smart contract sees the proof, verifies the proof, and it goes to the next stage instantly, because it has verified by cryptography rather than verified by someone else who would be watching.
Right. Okay.
Like in optimistic. So no, there is no such thing. Well, we could have, right? That's like Vitalik's points about like the training wheels and so on, and having multiple mechanisms. So you could say you have the proof and plus fraud proof, like this, someone that watches that has 1 hour to dispute the proof. So we could do that. Yeah. All right. Maybe let's move on.
Yeah.
So we were focusing. Let's focus now on the processor part, right? That executes the bytecode. So it looks like this. So the steps, they are like cycles of the machine. It's like time, basically. And at each time step, you have an instruction coming. So you have to read it. So there's a program counter, and that tells you which instruction in the bytecode you're supposed to execute now, and it loads it, verifies that it loaded correctly, and then execute it. So that's a trace. That's clear trace. Okay. Yeah. Then for each step of the machine, there is a like sub-circuit, let's say, that's going to verify its execution. So what does it do? It applies, a step. What does it do? It has to apply the side effect of this instruction. For instance, if it's push here, that's going to change the stack. It's a side effect. And the second thing it has to do, it has to move to step 2. So verify that it updates the states correctly between steps. And steps don't have all the same size. So some are like more complex than others and take more space, more witness space in the circuit. So what's inside of the already answered. So well, there are many more things. What's inside? Yeah, so the step has to support the different type of instructions that it could see at any cycle. So it's a sort of switch statement, right? Like looking at which opcode we have and do something different for each opcode. And then there's some space for the witness, and depending which opcode it is, there will be some logic, and this area of witness will be used by the implementation of that one opcode. Right. So that's what you have in a step, and this is really very similar to a regular CPU, right? So the pipeline is of CPU. It's a fetch instruction, decode instruction, execute instruction, and write back the result. So that's, you can identify this also in the zkEVM. For instance, you have the program counter, you have the stack pointer. So all very similar, very familiar for people who know CPUs. So there's the part which is like the state, as in a state machine. There's the part that looks at instructions, and there's the part that executes the instructions, including the side effects, like write to storage is a side effect. Yeah, and it does calculate the gas as well as part of this, the gas of this opcode. Yeah, what do you think?
One question I had, it's the stack. I'm trying. Sorry, I lost my train of thought. But yes, what about immediates? You have some instructions. Well, actually, there's very few of them, but there's push, for example. In the EVM bytecode, push is followed by the value that should be pushed on the stack.
Yeah.
How do you encode this in this case?
Actually, that's something that makes our life easier, right? As you said, in the EVM, there is very little of that, right?
Yeah.
Like in immediate. So immediate means that's an instruction. An instruction has an opcode. That's the family of instruction, and it might have an argument like this.
And inside the bytecode.
And that's inside of the bytecode. So that's basically the next byte, and maybe next. But the EVM ISA, so the instruction set, that I think it's only push that has this. I think all the others, they don't even have arguments. They don't have operands.
Yeah, there might be a jump, but I don't know if it's
maybe
it was debated. I don't remember, but yeah,
maybe there's a jump. I think we jump widths from the stack also.
Yeah, there's a jump I.
There's a jump immediate.
Yeah,
maybe. Yeah, but mostly the instructions, they are just opcode. So most of them. So it's much easier to decode. It's basically the simplest ISA before Turing machine, right? That's so that's really good. And your question was how do we actually handle, because there are some like this. You could have you have a push 16 or something with 16 bytes behind, and that's a separate circuit actually. Was it on my list there? Well, it's here. There's a bytecode circuit that does this. So that decodes the bytecode, and it recognizes that when the opcode expects an operand, like push one, next byte is like this. It decodes this and puts it into a regular table, like with a regular form that is easier to read. So the EVM circuit can just say, give me this index, and it gets the proper byte, and it gets the information that this byte is an opcode or it's an operand. So there's a dedicated circuit to reformat the bytecode and also calculate the hash of the bytecode. Yeah.
You got another question.
Let's see. How modular is your circuit arithmetization with every opcode of a circuit? So every opcode has an implementation in a big circuit. So the implementation is very modular, right? It's like maybe I could show somewhere. Let's see. I can look for some code just to show you how modular that is. You see that's oh yeah, I was showing the right screen. So you see that's literally like this. So this is very decoupled. So you have an implementation of each opcode here inside. So and then it's each one is in a separate file. So it's pretty modular. And that's all one circuit. Well, that's the one circuit with the opcode implementation, but the implementations, they rely also on those separate circuits. For instance, the bytecode one and some other helper circuits. That's not per opcode. What else could I say about this? This is, yeah, no, this is very, very modular design. And also it can be tuned, as I said, about performance of prover versus verifier. So someone's asking how we run Rust code on NVIDIA GPUs. It's not. So the implementation of a circuit like that, it might be fairly complicated to implement in Rust, but really what we implement is the verifier, right? Not the prover. Although there is, of course, an implementation of the prover, but on GPU it's different. And we program this in Rust, and it might be fairly complicated to generate the witness, but after that, the circuit that we described, it gets compiled into something much simpler. The form that it's compiled to is basically just a sequence of addition and multiplications. It's a long sequence of operations that are very simple. And that then is implemented not in Rust, but in the Rust CUDA, right? So
yeah, because presumably there's an LLVM backend that compiles the CUDA, I'm pretty sure.
Yeah.
And so if you have Rust, I mean, Rust is based on LLVM, so you could potentially write Rust code that calls the CUDA functions.
Yeah, it's a wrapper, right? So you have a core or kernel that's implemented in CUDA, but then your application, you write it in Rust and you call the kernels. Yeah. But again, you don't have to implement all the complexity of making the witness or the zkEVM in CUDA, right? Like this is all in Rust, and once the witness is generated, to go from witness to proof, that's much simpler operations. It's just a sequence of addition and multiplications and connecting them together. So it doesn't have to implement EVM stuff inside of the GPU prover, I believe. Maybe someone from the prover team on the chat to correct me if there's anything wrong, but I think that's how it works. So are these circuits written by hand? And how do you verify them? So yes, they are written by hand. We use the Halo 2 crate. And well, the strategy to write circuits is maybe it's a big community, and they have written first a circuit builder or constraint builder, right? That has a lot of helper functions. For instance, it has a helper function for push to stack, let's say, right, in the circuit builder, and then the implementation of opcode, they can reuse that. So it's still regular, like software engineering, right? When you do not repeat yourself and so on, and split everything into components. And how do you verify? So that's a big process, right? Of what it. So that's mostly my job and other people's, and we are also involved with basically all security firms out there. Yeah, so it's a big process. It's a whole new scale actually of audits because it's so many pieces to verify. So it's going to be lots of auditor teams, one after the other. So there's a timeline of that.
So can you just give a couple examples of tasks that you do to verify them?
Yeah, there are the puzzles, the zkEVM puzzles. I made a video where I explore the code. I don't know if I found the right solution or not, because I didn't go to the end. But yeah, how to verify.
I mean, yeah, just how do you say, for example, what would be an obvious example of something going wrong?
Let's see. Don't even have this. I have 14 slides about that. And each one has like 5 bullet points of things that can go wrong.
Okay, so for example, a wrong, like incorrect wiring would be an example.
Yeah, for example, when you program it, you I want to explain. So when you program this, you need witness. So witness, that would be like one of those cells, let's say, right? Let's say my task is I have program counter here, and I have a program counter in the next one, and I want to check that they are like PC plus 1. That will be next step. And so that's 2 cells of witness. And everywhere this PC, and this PC is also involved in other things, that is fetching the bytecode, right? So I need to make sure that it is the same variable, this PC, that does the bytecode and the next step, right? But when you program it, it's very easy to write a function that's some helper function, and it's very easy to use because it allocates everything it needs. But the problem is that someone else wrote another function which also allocates new cells. And so you might have this problem that you end up with 2 different cells for this PC variable, and they were supposed to be the same, right? So you have to make sure that you really use that everything is connected correctly, or that something must be equal. You don't forget to say it's equal, or use the same. You can forget range checks as well, because let's say one of those things needs to be a Boolean, needs to be 0 or 1. Very easy to forget, or it needs to be a byte, 0 to 56. Don't forget the range check. There's determinism, as I mentioned, like we want the entire thing to be deterministic. So if there is a way that you could take 2 parts and they will both be valid, that's not good.
Hey, I just want to jump on real quick because we only have a few minutes left in the hour. Yeah. There were a few questions that were asked sort of back at the beginning of the session. Yeah. I don't know if you want me to ask those or if you want to.
Sure. Yeah, go for it.
Okay, so one was, how do you see the efficiency of Scroll zkEVM change once ETH sharding is implemented?
So once you got all the prover things like really optimized and fast, and it's cheap to make proofs versus the size of the block, so it's cheap per transaction or per gas, then the bottleneck is storing the transaction on mainnet, so storing the transaction data. It's much cheaper than executing transactions, but it still has a cost. And I believe if sharding is about data, right? It's about data sharding.
Yes.
And that will make this cheaper. So you can have like very large rollups.
Right. So if I may just add a quick question, you might have heard of EIP 4844. That basically it's it's a way to reduce the cost, because I see you're pushing a lot of data. I mean, the transactions.
Yes.
Kind of the same question, but with EIP 4844, namely. Basically, do you need this or do you not need this?
Yes, it's an intermediary step to data shards, right?
Yeah.
So yes, same. Okay. Making the transaction data cheaper.
Mm-hmm.
Cool.
Because we need the data to be available, right? So,
another question was, what can a community do to improve Scroll?
What can a community do? So, got to be. So you can try it. So we have that's very useful. Try it. Try your smart contracts and tell us if it works. If your MetaMask works so testing, right? Generally testing. That's great. Then give feedback about how reliable that is. And you can join us also to work on it. Yeah.
Cool.
Or you work on it at the Ethereum Foundation as well.
One other question was, what does day-to-day work look like? Or what does the day-to-day work as a security engineer on an L2 project look like?
So that's reading a lot of code all day long, reading code and making checklists. And third is communicating. So I explained a lot. A lot of mistakes that happen or could happen, or yeah, I make lists of things to be careful about. Like which
all right, there was one last one. Oh,
I make lists. Very big lists like that.
Okay. There was one last one that was actually the first one, and it's very high level. What do you think is important for this project to survive for a long time?
Money.
Adoption, right? That's adoption. That's join the testnet and then the mainnet and deploy an ecosystem with all the DeFi's. And that's what's great about the rollups with EVM and contract compatibilities, that you can deploy a lot of ecosystem that can be composed, right? This is what Ethereum is all about, and also zk rollups, that you can compose with different kind of DeFi, with the different NFTs and all that, right? So you need all those projects to you want to be able to combine them all on the rollup.
And also,
I think that's the most important.
And also maybe all those GPU miners, if they realize they can finally use those GPUs again, that might make it
yeah, to make proofs.
Yeah.
Fantastic. Thank you both. Thank you, Aurel. Thank you for this great presentation and workshop all about Scroll.
All right. Thanks for having us.
Well, thank you.
Really fun.
Yeah. Cheers.
Bye.